Mr. Tarou, in this lesson we are going to be looking at and trying to help you understand relationships between variables. We do a lot of graphing in algebra and practically every math class you'll ever study. Once you get into like pre-algebra and such, we'll be graphing lines and parabolas and absolute value functions and many other types of functions. Ultimately, the end goal, after we learn how to find x and y intercepts and maybe the vertex of a parabola, we'll talk a little bit about identifying, at least visually, where graphs are increasing and decreasing and constant. After we apply and we learn all these sort of basic math concepts, you know, in the real world, those have to be applied to real-world settings. Like, if I want to see if how many, if I want to look at the relationship between how many hours my students study and their final grades, I could randomly select some of my students, ask them to do sort of an anonymous survey type situation, collect their data, display it on a plot, and then if that data follows certain, like there's a scattering of points, but if I notice that they're kind of straight, I can graph a linear model through those points of line, and that line might not intersect any of the real data points, but I could use it to analyze the relationship between hours studied and grades. And that's just because I'm in a classroom. It's an obvious example for me to come up. Maybe you can come up with some of your own. But the point of all of this algebra, all of this math that we're learning, all this graphing, is to ultimately, outside of school, model real-life situations. And certainly when you study statistics, that's all statistics is about, is using math, using equations to analyze and describe the behavior of real-life data. So in this lesson, we're going to really just focus on a lot of vocabulary. We're going to talk about what does it mean for a graph to be increasing, have a positive slope, or positively associated? What about if a graph is horizontal, or if a graph is falling to the right? What kind of vocabulary, what kind of language can we use to describe what's going on there? We're going to define what an independent and dependent variable is, and then end this lesson with 3 examples. There are going to be 3 sort of, fairly basic real-world samples that we're going to read. We're going to identify the independent and dependent variables, and then try and draw a sketch that graphically shows that relationship. So let's get on to the lesson. What does this graph mean or represent? With what is up on the board right now, it means absolutely nothing, okay? But I can read this graph left to right and start to describe some of the behavior of it. But before I get that, my wife is coming home, so let me pause and let her in, and we'll pick this back up. Alrighty then. So we can see that there are sections that rise to the right. There's 1, 2, 3, 4 of them. Sections that fall. There's 1, 2, 3, 4, 3 of those sections. And then there's a lot of sections in this graph which are horizontal, which means that as you read the graph left to right, there's no vertical change. It's just horizontal. So there's increasing, horizontal, and then decreasing. Okay, again, this has no context, so we're just going to pick apart some of the characteristics that we see in this, well, basically a piecewise graph. There's a bunch of little straight pieces. If a graph rises to the right, and you do want to read a graph left to right, just like we read our, English books. So if a graph does rise to the right, it is said to be increasing. So there is 1, 2, 3, 4 intervals in which this graph is increasing. And you can also say that in those 4 sections there is a positive slope. Again, you read this left to right and is positively associated. That's another, basically all 3 of these phrases I have underlined in green all really mean the same thing. It just depends on the context. Like positively associated would be language that you hear very often with application problems. Now let's see here. When you talk about, and I have other graphs where we do this very detailed. This is just really kind of like a vocabulary type lesson. When you talk about where a graph is increasing, you are talking about where it is increasing along the x-axis. So if this if this coordinate was 0, 0 and this coordinate was 5, 1, we would not say it increases from 0 to 1. We'd say it increases from 0 to 5. So the interval in which the graph is increasing, there's 4 of those intervals. Again, 1, 2, 3, and 4. And when describing those intervals, it would be describing where along the x-axis that graph is increasing. And again, when we get to very specific sort of, again, the actual math processes and formulas and such, we'll talk more about that later. Okay, so up to the right, positively associated, has a positive slope, and it is said to be increasing. If a graph is horizontal, it is said to be constant. Now, and that means it also has a slope of 0, and you may also read that there is no association, again for application type problems. Oh, and by the way, this graph is many things, okay? You can have a graph that only ever increases. You can have a graph, or if you look at, like in statistics, a scatter plot, where the scattering of points is really throughout the entire, well, I don't use too many. Well, we're going to define domain. Along the entire domain would be horizontal, and that graph would be constant. We have portions of this graph where we have horizontal slopes, again where the line is flat, if you will, and during at least those particular time periods, you could say that there's no association along those individual segments. But this entire graph has some places where it's positively associated, where there's no association, or where the slope is 0, or where it's constant. And then if a graph falls to the right, or identifying portions of where a graph falls to the right, then along those portions, or the entire graph, if such, is said to be decreasing, have a negative slope, or is negatively associated. Again, you can use that phrase even just in a pure mathematics formula type graph situation, but it is used a lot with application problems, word problems. So if a graph is falling to the right, again, read it left to right, let the x values increase from low to high. And what's going on with the y values? Well, if they're falling as x increases, then it's decreasing, negative slope, and negatively associated. And just like I pointed out the places where the graph had some positive slopes, there are some areas where this graph is falling to the right. And sections, let's say this is one interval along the x-axis where the graph is falling, where the graph has a negative slope, where the graph is negatively associated. But so at least in language and in just visually looking at the graph, we understand now some new vocabulary, but that still doesn't give this graph any meaning. It still doesn't give this graph any context. So I'm going to erase the board, and we're going to try and do that. To get to work, you leave your home and walk to the subway terminal. Subway is kind of like a train. After a short wait, you get on the subway car and ride to the terminal near where you work. You get off, you go to work, and then after work you pay for a taxi to go home. Kick your legs up, take a day, relax, think about how wonderful your day at work was. So reading that story, maybe you can kind of start visualizing what this graph really represents, or have some context to it. In other words, how does it represent to this real-world setting? Well, before we try and label it completely, we want to understand what an independent variable is and a dependent variable. An independent variable explains a change in another dependent variable. In many situations, you have control over the independent variable, and it is the input values. What would you be putting into an equation, say, and the numbers that you get out will be the dependent variable, or values. You want to place the independent variable on the horizontal axis, often just simply called the x-axis. This idea of, in many situations, you have control over the independent variable. In the previous scene, I talked about students studying, the amount of time they study, and their ultimate grade in my class. Again, when I collected that data and displayed it, and maybe if it happened to be a linear pattern, run a regression line through it, the students have control over the amount of time that they study. So in that case, the time studied in minutes or hours, or however it's being measured, would be the independent variable and go along the horizontal axis, or the x-axis. The dependent variable depends on another variable, the independent. It is a response, it is an effect, it is an output value that you get from an equation, and you're going to place that on the vertical axis. So back to this particular situation, what's going on? You're leaving your house, you're going to work, this could mean all kinds of things, but if we want to focus on just time passing through the day, and we see that we're starting off by leaving home, and we have a point here that it's at 0, 0. So it seems like when one something is 0, another something is 0, and if we focus on the fact that, well, we're traveling, and when we travel, that changes the distance we are away from where we start or maybe where we're going to. And traveling takes a period of time. Well, you know, you think of, well, if I'm traveling, like if I'm driving in a car or my bike, it's got a speedometer on it. I know how fast I'm traveling, how fast you're traveling. A lot of speed, at least especially in America, speed is measured in miles per hour. Well, the word per, pretty much in math, always means division, and so it's a division of two variables, distance and time. And again, you don't have to use miles and hours to measure distance and time, but in this case we are going to. So what is going to be the independent variable? Well, if you're late to work, you have thus sort of put some control over the fact that you're going to have a very short period of time to get there. And that period of time that you have to get there is going to help explain how fast, if you will, you need to cover that distance. So I think it makes kind of sense, and generally actually with math problems, if there is a variable of time, it's almost always placed along the x-axis. So on our x-axis, we're going to be measuring time in hours. It's not really enough just to label the x-axis as time or whatever that independent variable is going to be. You need to indicate a unit of measure, whether it's right on the axis like I've placed it or you've put it somewhere else as a key. And it seems like, again, we're starting off with a y value or a response value of 0, and then there's a value that stays constant, which is clearly, you know, larger, and then it goes back to 0. So it would seem to make sense that the y-axis, the vertical axis, is going to be the distance from home. And just to go with the idea of like our car speedometer or bike speedometer, that would be in miles. And now we kind of see a complete picture. You're walking until you get to the subway, and then there's a horizontal piece, and then you get on the subway, and it's going to, of course, travel faster than you could walk. And that increase in speed, that faster subway compared to how fast you're able to walk, means that over a short period of time, you're going to be able to cover a greater distance. So that increase in the slope is representing a faster speed, or later when we actually start running numbers and calculating slope, that increased steepness in the graph is going to give you a larger value, a increased value of slope. And in the case that slope, another idea of slope is a rate of change, which is just sort of a general expression, but in this case it really is a rate of change in which your distance from home is changing over a period of time. What do you think these little segments, these little flat segments are? I mean, I'm away from the camera. I step forward and then I stop. My distance towards the camera is not changing, but time's still going by, right? You can see the little ticker at the bottom of this lesson. So this is simply where you're standing still. You know, whether you're waiting for the subway stops to pick up more people along the way as you get to work. For some reason here, the line's not as steep, and it seems like maybe the subway's not traveling as fast. It's not, you know, it's taking a longer period of time to cover maybe about the same distance. And then at work, you're moving, you're expending energy, but your distance from home is staying constant. Constant, right? As time is changing, that slope right there is 0, and then of course we have some negative slope, some periods where time is going by and the distance from home is decreasing. Again, we're not crunching numbers, we're just doing some basic vocabulary here. And this is just in case I said it and you didn't catch it. In the setting, time traveling is explaining how far you are from home. Thus, the distance from home is the dependent variable and the time is the independent. Let's get on to those 3 examples where you're going to create a sketch, to match the given setting after we identify the independent and dependent variable. Bye! So, you know, you don't have to work your whole life. what you need to do, if you don't want to work your whole life, what you need to do is make the most of the years that you are working. And you need to do that by saving a little bit from every paycheck for retirement. If you earn 7% on your money that you've saved for retirement, it will double about every 10 years. So your money can help make you more money instead of you having to, physically, labor over every dollar that you earn. You allow the money to grow on itself. Okay, so in this scenario of you saving for retirement and that money growing by 7% a year, if you could manage that through investments over a long-term average, what is going to be the independent variable? What are the variables? If you earn 7%, okay, that's a percentage is a type of variable, and if I would actually given you formulas and not just talking about relationships between variables and some vocabulary, we could use that percent to actually calculate something. But then we go on to read, it's talking about an amount of money that we have for retirement, and it will double about every 10 years. So the other variable has something to do with a period of time. So the independent variable is what you have control over if that sort of fits the real world setting. And certainly I can control when I start saving for retirement. Do I want to save early when I'm in my late teens and 20s, or am I going to wait a little bit later in my life to start saving for retirement? So I have control over that period of time. So the independent variable is, well, time. And what's the dependent variable? Well, the dependent variable is going to be how much you have in savings, the money that you have for savings, that is going to be dependent on how long, well, not only how much do you save, but how long what you did save has to grow compoundly on itself. So we're just going to put money, or I could just say, savings as my dependent variable. And then sketch a scenario. Okay, well, my scenario, what would this look like as a sketch? Well, where does the independent variable go? It goes on the horizontal axis, the x-axis. So the horizontal axis is going to be time, and that is going to be in terms of years, and that is the phone, so I'll be right back. And the y-axis, you could, put retirement savings, or just for purposes of not having to write too much during our lesson, I'm going to write money. And the unit of measure for this response variable, the money, is going to be, at least where I live, US dollars. So I've got my x and y axis, or my horizontal and vertical axis labeled with those variables and the units of measure. And again, no numbers, so let's just sort of say at time 0, we have so much. And then this is about it doubling every 10 years. So 10 years later, it's doubled. So now it's only that much. And another 10 years later, it has doubled again. So now it's this much. And 10 years later, it's doubled again. Well, I don't know what that tick mark really means. I haven't put numbers on my scale, but if it is 2, then 2 doubled is 4. So now we're here at 4. And another 10 years later, it has doubled again. Well, it was at 4, and now it's going to be 4 higher, which is going to be 8. And this is going to continue on, and the graph is not going to be linear. It's actually kind of curving up. Now, in the real world, bank interest loans or interest rates, market performance, the stock markets and such, is one country doing well, or is another country sort of defaulting on its loans and having problems? Certainly, we can look back historically through financial graphs and information and see that our economies are constantly changing. Sometimes they grow, sometimes they don't grow. There's a word for this, but basically shrink. There's good times and bad times, right? And so in the actual data, it might be sort of gyrating all over the place, but we have like this mathematical model. If you could, on average, over a long period of time, average 7% on your savings, this is the sketch of how these two variables of time and money are related to each other. Now I'm going to bring up another example. I'm going to not actually explain it through. I'm going to hopefully have, I'm asking you to pause the lesson and read the scenario and try and identify the independent and dependent variable and sketch the scenario, and then on the sketch include the units of measure next to your independent and dependent variable like I have, and then we'll check and just sort of, I'll talk through how I interpreted the little scenario and my answer. So we were driving and not staring at the computer, but every once in a while glancing over, realizing that as we drove at different speeds on our highway, 40 miles an hour, 50 miles an hour, 60 miles an hour, 70 miles an hour, that the mileage that you were getting from the readout on your car was different, the miles per gallon. So you have your foot on the gas pedal, right? You are controlling how fast you are driving. So thus the independent variable is going to be speed, and the dependent variable, well, you're controlling the speed, and somehow the mileage is being affected by that. Now, maybe you're not old enough to drive a car, but you're probably riding a bike, right? So if you ride a bike at 10 miles an hour and you ride a bike at 20 miles an hour or 25 miles an hour, whatever the fastest is, the fastest speed that you can attain, which one takes more effort? Well, as you go faster, you have all that wind hitting you in the face and your chest and everything else, your bike, and it's trying to slow you down, so it takes more energy to ride your bike faster. Well, the same thing is true in a car, or maybe you're old enough to drive. That wind resistance, among other things, is trying to slow the car down, thus taking more energy to push it into and through that wind. So the mileage is, of course, the dependent variable. Now the speed, I said the mileage was in miles per gallon. That's what that MPG is supposed to stand for. And thus we're still doing this is miles and hours idea. So our speed is going to be in miles per hour. The mileage, miles per gallon. And what did your sketch look like? And I boarded this so that we were already in motion and already like on the highway driving a particular speed, so we don't have to talk about, well, if you're sitting still, your mileage is 0, and how the efficiency of your car changes as you go from 10 miles an hour, 20, 30, 40, 50 miles an hour, and so on until you just speed up. So we're already going at a particular speed, let's say 50 miles per hour, and maybe you're thinking of an initial speed that's something different, but we are already in motion, and whatever that motion may be, that initial speed, again, thinking about riding a bike, the difference between how you feel trying to exert that energy to ride 10 miles an hour versus 25 miles an hour, it takes more energy to ride at a faster speed. So as your speed increases, I'm guessing that we probably have some kind of relationship where the mileage is decreasing. Now, we could make a straight line. We could maybe think of this line kind of curving out. This is just the very beginning study of how variables are related to themselves. I would have a bit of a problem if you drew a straight line and just stuck an arrow on it, because that would indicate that it was going down forever. Well, if it goes down forever, at some point you're going to cross through that horizontal axis and that line is going to drop below it. Well, that means that your mileage is actually negative? Would that mean that as the faster you went, your gas tank actually started to fill up? No. And I'm not sure if there would ever be a scenario where you're moving, where your mileage would be 0 miles per gallon. So really, probably this type of scenario is some kind of curve where ultimately, no matter how fast you go, or as your speed increases, that mileage approaches 0 miles per gallon. But if you're moving, how can you be 0 miles per gallon? You're moving. But at any rate, that's getting a bit more technical. We do have an independent variable on our x-axis, a dependent variable on our y-axis or vertical axis, and if the car is already in motion and we're increasing that speed, hopefully we have some idea now that the efficiency, the mileage, would be decreasing with that increased speed. Third example. last example. You would like to make some money selling bird feeders. The initial cost for the tools is $250, and the material cost for each bird feeder is $10. What is our independent variable? What do you have control over? Well, is it the total cost, or is the total cost going to depend on how many bird feeders you make, right? So the independent variable is the bird feeders. And actually, specifically, I have no idea why I wrote birds in uppercase and feeders in lowercase, but it's the number of bird feeders. Now, if there was really like a unit of measure, I guess I would just write that the independent variable is bird feeders, but you know, it's not like we're measuring it in miles or inches or kilometers or something like that. It's just, I'm just counting them. It's how many I've made. And the dependent variable then, well, the number of bird feeders. Well, I'm talking about I want to make some money, but I never talk, there's nothing in this scenario that describes how much you're going to sell each bird feeder for. It's just how much it's costing. So the dependent variable is the total cost. Okay, so we have our independent variable on the x-axis, so number of bird feeders. Now, if I was making thousands of bird feeders, by the way, I would say that the x-axis is bird feeders and then parentheses write in thousands or something like that to keep the numbers smaller. But if it's just a handful of bird feeders, that is sufficient. And then the y-axis, the vertical axis, is going to be the, you know, for the dependent variable, and that is the total cost. And of course, we're going to measure that in dollars. Now again, I'm going to go a little bit more depth with this particular one, and well, I don't know if I'm going to be reviewing for you because, you know, you're not my student, right? I mean, you are kind of like you're watching my lesson, but I don't know if you've taken pre-algebra, algebra. I don't know if this is a review. So this may be a review. It may be a preview of what you're going to see as we get into, because I'm making this lesson for the beginning of my algebra course. You would like to make some, well, the first scenario was about money and interest and that money growing compoundly. And certainly where I'm making this lesson, and we'll be using it for my classes, we haven't covered compound interest yet, or exponential growth and decay. And the second problem, well, I don't even teach, you know, you would need to know physics for that and how, you know, the relationship between speed and air resistance and how that changes. But I think it made sense that, you know, our mileage would decrease as our speed increased. But this one, this is something that you definitely, the scenario is something that you would have studied in pre-algebra, or if you're beginning pre-algebra, you will be doing soon, and that is a linear relationship. So I don't want to get in depth into creating equations and graphing lines, but I'm going to give you a little bit of a preview here. We have, well, clearly our total cost is going to go up with the more bird feeders we make, and the initial cost means that before you even make the very first bird feeder, it's going to, if you're going to do this project, it's going to cost you $250. That initial cost of $250 is what we will be learning, or I'm reviewing with you, I'm not sure, is a y-intercept. It's where the line, which is going to model the cost that these bird feeders are going to be to make, that initial value is going to be $250. And how much would it cost if we didn't make, how much would we be spending if we didn't make any bird feeders? Maybe you started this project and changed your mind. Well, that would be, let's see here, color I haven't used yet. If I make no bird feeders, then it would be $250. If I made one bird feeder, then, let's do a little arrow here so you know what these numbers represent, then that would be $250 plus 10. If I made two bird feeders, that would be $250 plus 10 plus 10. And if I made three bird feeders, well, then that would be $250. And maybe I'd be a little bit too lazy to write 10 plus 10 plus 10. Or maybe because the numbers are so small, it'd be like, well, that just cost $30. Well, how are you getting the $30? Well, that's going to be plus 3 times 10, which would be $250 plus 30 would be a total cost of $280. And by the way, if you don't understand why I keep adding these tens, well, it says here that every bird feeder I make is an additional $10 of cost. That's the material cost for each bird feeder that we make, and then I'm going to make them with these tools that initially cost me $250. Well, if you look at this pattern here, I have a total cost of $280, which is equal to, or found by doing 250 plus $10 times how many, or the number of bird feeders we've made. And that's how a normal person talks. A mathematician or an algebra teacher might go, well, that means y is equal to 250 plus 10x. And then you look at that and you're like, x's and y's, they don't get that. Well, the y would be our total cost and the x would be the number of bird feeders. And by the way, I have an algebra lesson for, and I think there's like 4 or 6 examples where we read word problems and just try and develop the equation that represents that setting. Because setting up word problems is really the most difficult part about them. And then the algebra, you'll probably learn, is the easier part of the question. So we have at 0 number of bird feeders a cost of $250, and then from there, every time I made another bird feeder, it just added another 10. So whether I'm going from my 10th to 11th bird feeder or my 100th to my 101st bird feeder, it's just going to always, every time I add another bird feeder, add $10. So thus, the sketch of the scenario will be a line, because this case is going to be linear. Every additional bird feeder costing an additional $10 with a y-intercept of 250, and it just goes up forever. And if you have studied lines, it's maybe a little bit of review. If you haven't, it is coming up in our algebra class. But for now, just understanding the relationships between variables and defining independent and dependent variables and what increase and decreasing intervals represent, all that good stuff, that is the end of my lesson. So, I'm Mr. True. Go do your homework.